Hello guys, and welcome to another calculus video. Today we're going to be checking out some awesome infinite sums involving the zeta function. It's sort of in response to this comment that one of my viewers left on a recent video on the Riemann zeta function, or on a very similar video where we took sums with the Riemann zeta function, but in that video we were dealing with zeta of even numbers, which, as it says in the comment, are a lot easier than odd numbers. So, as you can imagine, in this video, we're going to tackle some sums which involve the zeta function of odd numbers. So it's going to be a little bit more difficult. We're going to have sort of extra multiplying terms that we're going to have to deal with, but overall it's going to work out for us. We're going to get some awesome results. And yeah, so sit back, relax, and enjoy the video. So the first sum that we're going to be evaluating is the sum from n equals 1 to infinity of n times zeta of 2n plus 1 minus 1. And of course we need to start at n equals 1 because at n equals 0 we're going to have zeta of 1, which is infinity. So we're going to just rewrite this the way we always have, the sum from n equals 1 to infinity of the sum from k equals 1 to infinity of 1 over k to the 2n plus 1, right? And we're just going to kind of reorganize this and put a minus 1 right there, right? And this minus 1 right here, we can actually combine this because as you can see, when k equals 1, 1 over k to the 2n plus 1 is just going to be 1. So we can remove this and make this the sum from k equals 2 to infinity. And then we can go ahead and bring inside that n. So if I just go ahead and reorganize this a little bit, it's just going to be the sum from n equals 1 to infinity times the sum from k equals 2 to infinity of n over 2 to the 2n plus 1, or k to the 2n plus 1. Next, we're just going to exchange the order of summation, and then we can actually write 1 over k to the 2n plus 1 as 1 over k to the 2n times 1 over k. Then we can bring this 1 over k outside because this inner sum is a sum on n. And so a sum on n has nothing to do with k, right? So we don't need to worry about that. Then this is just going to be n times 1 over k squared, all raised to the n power. If we go ahead and take our geometric series, which is equal to the sum from n equals 0 to infinity of x to the n, differentiate both sides with respect to x, we can see that this sum is actually really easy to evaluate. I'm just going to multiply on both sides by x. And so in this case, our x is 1 over k squared, so we can go ahead and plug that in into this sum to figure out its value. So we're going to get the sum from k equals 2 to infinity of 1 over k times 1 over k squared times 1 minus 1 over k squared squared. We're going to multiply by k to the 4th on the top and bottom, and we're going to end up just with k on the top and k squared minus 1 squared on the bottom. Now, after this step, all we have to do is do some partial fractions. In order to do this, I'm going to go ahead and just skip some steps because I already know the answer. I've done the partial fractions before, so you guys could do it normally, or I'm just going to write this as 1/4 times 4k, right? So we can write this as 2k plus 2k. So we can actually write this as k squared plus 2k minus 1, or plus 1, minus k squared plus 2k minus 1. And as you can see, that cancels perfectly. And of course, this left part is just equal to k plus 1 squared, and this right part is just equal to negative k minus 1 squared. And so overall, the partial fractions result for our sum, we're going to have the sum from k equals 2 to infinity of 1 over, so k plus 1 squared over k squared minus 1 squared, since this bottom is actually just equal to k plus 1 squared, k minus 1 squared. We're just going to end up with 1 over k minus 1 squared minus 1 over k plus 1 squared. And this is actually just a telescoping series. So if we go ahead and evaluate this telescoping series, it's going to be pretty simple. 1 over k minus 1 squared minus 1 over k plus 1 squared. We can go ahead and just write out the first few terms. We're going to end up with 1 minus 1 over 3 squared plus 1 over 2 squared minus 1 over 4 squared. Oh wait, this is all times 1/4 also. Plus 1 over 3 squared minus 1 over 5 squared plus 1 over 4 squared minus 1 over 6 squared, and so on and so forth, right? I'll put a dot, dot, dot. As you can see, this is going to cancel with this is going to cancel with this, and everything after this is just going to keep canceling, right? All the way up to the last term, which would be 1 over n squared, limit as n goes to infinity, which just goes to 0. So these are the only two terms that will matter. So it's just going to be 1/4 times 1 plus 1/4, which is equal to 5/16. And overall, this looks like a pretty simple, straightforward answer, right? But if you think about it, the original sum that we took was the sum from n equals 1 to infinity of zeta of 2n plus 1 minus 1 times n. And so we're summing up all these odd powers of zeta, we're subtracting, or odd zeta functions, we're subtracting 1, and we're multiplying by n. And remember that none of the values of zeta of odd numbers are actually known values. They're all like transcendental numbers that have no representation, even using pi and e and all our special functions. And so we're adding up all these very, very complicated unknown numbers, subtracting 1 and multiplying them by n, and we actually end up with something that's not transcendental, not something that just uses elementary functions but has transcendental numbers. It's not even irrational, it's actually turns out to be a perfectly rational number. Now that is something that is just truly amazing to me, and it's just kind of part of the magic of math, of how it all ends up working out in magical ways. So yeah, so that's our answer. Now let's move on to the next problem. The next problem we're going to be evaluating is the sum from n equals 1 to infinity of 4 to the negative n zeta of 2n plus 1. This is going to be pretty straightforward. We're just going to use the same strategy we used last time. So the sum from, or sorry, we still have n on the outside. N equals 1 to infinity of the sum from k equals 1 to infinity of 4 to the negative n, 1 over k squared, k to the 2n plus 1. So we'll end up with the sum from k equals 1 to infinity of 1 over k times the sum from n equals 1 to infinity of 1 over 4k squared. The sum of a geometric series is super simple. It's just the first term over 1 minus the common ratio. So that's going to be pretty straightforward. We're just going to have a sum from k equals 1 to infinity, 1 over k times 1 over 4k squared over 1 minus 1 over 4k squared. If we go ahead and simplify this by multiplying by 4k squared on the top and bottom, and we can go ahead and just factor this whole bottom and write it as a really simple rational function as 1 over k, 2k minus 1, 2k plus 1. Then we're just going to go ahead and do partial fractions, doing the cover out method, which is super easy to use. I'm just going to go ahead and do that super quick and let it fast forward. So after doing partial fractions, this is what we'll end up with. And then I'm just going to go ahead and split this up into negative 1/2 over k minus 1/2 over k. And now we can go ahead and split this into two different convergent sums. That's a mistake I made in a previous video. I split something into two separate divergent sums and then added them together, but in this case they're going to remain convergent, so it'll be okay. So we have the sum from k equals 1 to infinity of negative 1 over 2k plus 1 over 2k minus 1 plus the sum from k equals 1 to infinity of negative 1 over 2k plus 1 over 2k plus 1. Alright, so these two sums are pretty similar and they're going to have pretty much the same result here, but let's just go ahead and evaluate them both. So for this first sum, we can just go ahead and start writing out the terms here. As you can see, this is going to end up being all the even numbers, this is going to end up being all the odd numbers. So we're going to have 1 minus 1/2 plus 1/3 minus 1/4, and it's going to keep on alternating like that forever. This is a very famous sum, and hopefully you guys know this one. This one is equal to ln2. You can also prove that using the natural log power series, but overall it's just a famous sum that I know off the top of my head. This sum is almost the same thing. We can just write negative 1/2 plus 1/3 minus 1/4 plus 1/5. And overall this looks a little bit wonky, but as you can see, it's just the same exact sum as this one, right? It's just missing that first term, that 1. So it's going to be equal to ln2 minus 1. So if we add these two together, we'll end up with ln2 plus ln2 minus ln(e). So overall, we can write our answer as ln 4/e. So that's the last sum for this video. Thank you for quote-unquote challenging me to do this video, even though I know that wasn't your intention. Yeah, I hope you enjoyed this video. I had a lot of fun, and I'll see you next time.